Even though the SN2 reaction is one of the most simple mechanisms we will encounter, it needs to be understood thoroughly in order for us to be ready for more complex systems. In order to become familiar with how mechanisms are established in general, we must consider what experimental evidence is on hand and how we may use it as clues. In this reaction between methyl bromide and ionic cyanide, we know that the reaction goes completely to products. If more NaCN is added, the reaction goes faster. Likewise, if more methyl bromide is added, the rate increases. If a chiral alkyl halide is employed and the leaving group is at the chiral center, the configuration of that chiral atom is inverted during the reaction. Additionally, the rate of the reaction is sensitive to the steric environment at the alpha carbon, with increased crowding slowing the reaction down. Importantly, this reaction slows down if polar solvents, especially those that are capable of hydrogen bonding, are used. So, what does all of this evidence tell us, and how does it lead to a conclusion about the mechanistic pathway from starting materials to products? Firstly, if this is a potentially reversible process, and the reaction proceeds completely to products, then the products must be much more stable than the starting materials. Then, if the rate of reaction increases, by adding either more nucleophile or more electrophile, then the rate-determining step for the reaction must be bimolecular. Since only one bond has to form, and one bond has to break here, both may occur in a single bimolecular step. The inversion of stereochemistry also infers a concerted process, in which the nucleophile bonds to the alpha carbon at the same time as the leaving group detaches. A stepwise process, in which events occur sequentially, would not give just one organic product. The fact that the reaction slows down, with increased crowding of the alpha carbon, points to that attack at carbon being rate-determining. Finally, the reaction slowing down in polar, and especially protic, solvents substantiates the idea that the nucleophile attacking the electrophilic carbon is the key event here. We now have to distill all of these experimental facts down into a mechanism that agrees with the data. However, we only have two choices for the pathway. It will either be concerted or stepwise. A potential stepwise route might involve the leaving group breaking away first, and then the nucleophile attacking the intermediate. This would not give an inverted product exclusively, however. It would also not agree with the rate data observed, since loss of the leaving group would be a unimolecular process. The only pathway that meshes with all of the data collected involves a concerted displacement of the leaving group by the nucleophile in one step. So, the accumulated evidence leads to a concerted process. Now, we need to include some curved arrows to describe how the bonds are formed and broken. Since only two events occur here, one arrow describes the bond forming between the nucleophile and the electrophile, while a second arrow shows how the leaving group detaches from the electrophile. As the mechanisms get more complicated, more arrows will need to be included. Let's summarize how the experimental evidence leads to the proposed mechanism. Firstly, the rate equation is bimolecular, so both nucleophile and electrophile are present in the transition state of the slowest step. Since this is a simple swap of two groups, with only one bond being formed and one being broken, all of that may be achieved in a single step. The observed stereochemical inversion at the electrophilic carbon is explained by the nucleophile lone pair docking with the vacant anti-bonding orbital on carbon. This leads to a linear relationship between nucleophile and leaving group in the transition state. Also, the isolation of only the inverted product precludes any intermediates being formed, since they would most likely be flat and be attacked from two directions to give two products. The fact that these reactions are slower when more crowding is present at the alpha carbon agrees with the rate-determining step involving the nucleophile attacking the electrophile. And, finally, polar, and especially polar protic solvents, would stabilize the nucleophile and, as is observed, slow the reaction down. Overall, the accumulated evidence leads to the simple, one-step pathway known as the SN2 mechanism,